Good evening, all. Welcome to today's live discussion session for the NPTEL course Water Supply Engineering. I am Reshma R, Research Scholar from Hydraulics and Water Resources Engineering Division, Department of Civil Engineering, IIT Madras. So we shall wait for 2 more minutes and then we'll start the session. I'll share my screen. Hope it is visible to you. Okay, we'll see the first question for today's session. On the basis of degradation nature, water pollutants can be classified as option A, conservative and non conservative pollutants, option B, geogenic and biogenic pollutants, option C, chemical sorry, chemical or physical pollutants, and option D, none of the above. So, on the basis of degradation nature, how do we classify water pollutants? Okay. Yes, as we have the answer in chat box, it's option A, conservative and non-conservative pollutants. So on the basis of degradation nature, water pollutants can be classified as conservative and non-conservative. Conservative is also known as non-degradable or non-reactive. Ag- Whereas non-conservative is also known as degradable or reactive pollutants. So on the base of degradation, we have conservative and non-conservative pollutants. Now, we have several other bases for classification of water pollutants as well. For example, if we consider the first one, that is on the basis of pollutant sources. If we classify the water pollutant based on their source of origin, we have four different kinds, namely industrial pollutants, agricultural pollutants, urban pollutants, and natural pollutants. So we had one option in the question that geogenic or biogenic pollutants, they are nothing but natural pollutants. So they come under the classification based on the source of pollutant. Based on the source of origin, we have industrial, agricultural, urban, and natural. As the name suggests, if the source of origin is an industry of any kind, that pollutant can be classified as industrial pollutant. If it is from agricultural field, then it is agricultural pollutant. If it is from an urban land, then it is urban pollutant. If it is a naturally originated pollutant, then it is natural pollutant or biogenic or geogenic pollutant. Now, the second classification is as we saw earlier based on the degradation nature. We have degradable or non-degradable or conservative and non-conservative pollutants. The third classification is based on the physical and chemical characteristics of the pollutant. On the basis of physical and chemical characteristics, we have physical pollutant, chemical pollutant, and biological pollutant. Moving on to the second question. The major routes of exposure to water pollutants in humans are: option A, inhalation and dermal exposure. Option B, only through inhalation. Option C, transfer across placenta. Option D, ingestion and dermal exposure. So, which are the major ways through which water pollutant enters into a human body? Which are the ways in which water pollutants enter into human body? Yes, it is option B, ingestion and dermal exposure. Typically, exposure to water pollutant occurs either by ingestion or dermal exposure. Ingestion means through mouth, and dermal exposure is through skin. So either through skin or or an intake through mouth will cause an entry of water pollutant into a human body. So the routes of exposure for water pollutants are: typically, exposure will happen either by ingestion or by dermal. So, ingestion means it is oral route. It can occur when we consume contaminated water or food items that is prepared using a contaminated water. Whereas the second one, that is dermal exposure, as I said, it is through the skin. This results when our skin comes in contact with a polluted water body, either during bathing, washing, swimming, or any other works, maybe some office related works, some laboratory works, or some field works. So, exposure to water pollutants through inhalation is actually not relevant for human beings. And a transfer of pollutants across placenta is also a minor route. So the major one is is either through ingestion or through skin, that is dermal. Moving on to question number 3. Acute or short term exposure to relatively high levels of contaminants is least likely to cause health conditions like: option A, asthma attack. Option B, headache. Option C, cancer. Option D, eye irritation. So, if we are exposed to acute or short term high level of contaminant, it is least likely to cause which of the health condition? Yes, the correct answer is option C, cancer. So, if we are having an acute or short term exposure to relatively high levels of contaminants, it will lead to acute health conditions like asthma attack, headache, or eye irritation. But if we have a chronic exposure, that is a long term exposure to that particular contaminant, then it can lead to chronic diseases like cancer. If it's a short term exposure, it will only cause eye irritation, asthma attack, or headache. So, acute exposure or short term exposure basically means minutes to days, and this will only result in acute diseases to extreme, that is the maximum extreme possible from an acute exposure is asthma. Whereas chronic exposure means an exposure that is over long years to lifetime, that will cause chronic effect. For example, cancer, chronic obstructive pulmonary disease, neurological problems, etc. Also, chronic pollution is often not confined to a small area. It may go undetected for a long time, and it is more difficult to rectify than an acute pollution effect. All right. So, moving on to the next question. Question number 4. Which of the following is a physical water quality parameter? Option A, order. Option B, temperature. Option C, total solids. Option D, all of the above. Which of the following is a physical water quality parameter? Which of the following is a physical water quality parameter? Yes, it is option B, all of the above. Temperature, color, order, turbidity, conductivity, total solids, suspended solids, dissolved solids, fixed solids, volatile solids, all these are common physical water quality parameters. All right. So, the next question. Electrical conductivity of water is expressed in the unit of option A, Siemens per meter, option B, Siemens, option C, Siemens meter, option D, none of the above. What is the unit of electrical conductivity of water? What is the unit of electrical conductivity of water? Okay, yes, option A, Siemens per meter. So, electrical conductivity of water is measured using conductivity sensors, and it is expressed as Siemens per meter or S by M. Now, moving on to the sixth question. A 10 ml of pungent water sample requires 190 ml of pure water to make it odorless. Determine the threshold odor number of the water sample. Option A 20, option B 10, option C 19, option D 200. So we have 10 ml of pungent water sample and we need 190 ml of pure water in order to make this pungent smell disappear. If that is the case, we are asked to determine threshold odor number. Okay, let's see how to solve it. I have got answers as option A. Yes, it's option A. So we are given that the total volume of pungent water sample is 10 ml and the amount of pure water required to make our sample odorless is 190 ml. So by the formula for threshold order number, we have threshold order number is equal to volume of sample plus volume of pure water needed to remove any odor divided by volume of sample, which is equal to 10 plus 190 divided by 10, which is equal to 200 by 10, or it is equal or 20. So that is option A. So next question, question number 7. Identify the correct pairs of water quality parameters and their method of estimation. Option A, microbial water quality, most probable number, volatile solids, titration with EDTA, option B, alkalinity, titration with EDTA, turbidity, scattered intensity of light measured at 90 degrees, option C, total solids, gravimetric analysis, hardness, titration with EDTA, option D, total solids, scattered intensity of light measured at 90 degree, microbial water quality, most probable number. Okay, so I have got answers one as B and one as C. Okay, let's see what is the correct answer. The correct answer is option C, total solids gravimetric analysis. Hardness is measured with titration with EDTA. So, microbial water quality is the most commonly applied parameter for microbial quality testing of water. So, in order to identify the fecal contamination of water, we use Escherichia coli or fecal coliforms. Escherichia coliform bacteria or fecal coliforms is used as an indicator for fecal contamination of water, and that is commonly known as E. coli. Solid analysis is always done using gravimetric analysis. So, for the determination of total solids, we go for gravimetric analysis. Coming to hardness, hardness is tested by titration with EDTA solution as titrant. However, we have test strips and instruments separately as well, which measures calcium and magnesium. That is also being used, but the most commonly adopted method for determining hardness is titration with EDTA. Alkalinity is also measured using titration, but with standard acids. Also, the titrant is different. Now, coming to turbidity, turbidity is measured as the intensity of light transmitted or as the intensity of light scattered at 90 degree, either transmitted or scattered. The process is termed as nephelometry since we use nephelometry instruments, and the unit of turbidity is nephelometric units or NTU. There are different turbidimeters for the measurement depending upon the range of turbidity to be measured. Okay, so moving on to the next question. The mechanism used to determine heavy metals in water is option A, flame atomic absorption, option B, inductively coupled plasma, option C, mass spectrometry, option D, all of the above. So, which of the mechanism is used to determine heavy metals in water? Which of the method is used to determine heavy metals in water? Okay. Option D, all of the above is the right answer. Metals can be determined using flame atomic absorption, electrothermal atomic absorption, inductively coupled plasma, or IPC or mass spectrometry. So we'll see each one of them. Flame atomic absorption is a common technique to determine metal and metalloids in environmental samples. For example, water sample. So it's a reliable and simple to use technique. When a liquid sample is drawn into a flame, sample atomization will happen, and that particular flame itself will serve as a sample holder because the sample is now atomized, and as the light passes through these atomized sample or the atoms and the flame simultaneously, absorbance of the light is calculated. The excellent bright line source for most of the elements determinable by atomic absorption is hollow cathode lamp. And here, in this method, we select the appropriate wavelength for the light, as well as the amount of light will be varying, and standard curves are available from which we can measure out the amount of light absorbed. So this particular method will give the metal concentration in parts per million. So this one is the most commonly adopted method, wherein we are utilizing a atomization method. The liquid sample is basically atomized using a flame, and then the amount of light absorbed is calculated. Next one, inductively coupled plasma. An inductively coupled plasma or transformer coupled plasma, it's a plasma source in which energy is supplied by electric currents produced by electromagnetic induction. Electromagnetic induction is nothing but time varying magnetic fields. That is, whenever that like the Faraday's principle of electromagnetic induction, the same principle is utilized here for the determination of metal or metalloids. So this is a precise method for measuring the individual elements that make up a test sample. The only drawback is this particular method can be adopted only on liquid samples. So the metals should be digested from its solid form. That is, whatever the sample material is, if it is in a solid form, we have to convert it into liquid. Only then we can apply this particular method. The third option was mass spectrometry. So, inductively coupled plasma mass spectrometry, or simply mass spectrometry, will use inductive. If it is a inductively coupled plasma mass spectrometry, it will use inductively coupled plasma to ionize sample. Like, we have different types of mass spectrometry depending upon the method that we use to ionize the sample. Since that is beyond the scope of the syllabus, we are not going into that. So here also what happens is basically the sample is atomized, and then we have atomic and small polyatomic ions which are then detected. This method is actually useful when it comes to detection of metals at very low concentration. Also, it can detect different isotopes of same element, making it a versatile tool in isotopic labeling. When we compare mass spectrometry to atomic absorption spectroscopy, this has a greater speed, sensitivity, as well as precision. So the next one is electrothermal atomic absorption. So what is happening in all the methods is basically we are atomizing the liquid. From the first method to this one, we are basically atomizing the liquid. Here also, we are atomizing the liquid, but instead of direct flame, we are atomizing using electrically heated atomizer or graphite furnace. Instead of that lamp or a flame, we are using electrically heated atomizers. So, in the graphite sample tube or the furnace, we'll apply the sample volume and then the sample is heated. So, this will happen in three or more stages. First, the sample will be dried, then, charring happens where organic matter is destroyed and the rest material is volatilized. And finally, a high current heats the tube to incandescence and atomizes the element being determined. So, if we need any other steps to speed up charring and drying, that may be added, as well as to clean and cool the tubes. So, the resultant ground state atomic vapor will absorb the monochromatic radiation, and then the amount of monochromatic radiation absorbed or the transmitted radiation absorbed or transmitted, it will be detected by a photoelectric detector. Now, once this transmitted radiation is calculated, the inverse of this particular value is related logarithmically to the absorbance, which is directly proportional to number of density of vaporized ground state atoms. So that is how we detect the quantity of metals and metalloids. Okay, now coming to the next question. Question number 9. Winkler method or azide Winkler methods are most commonly used to determine option A, dissolved oxygen, option B, chemical oxygen demand or COD, option C, biochemical oxygen demand or BOD, option D, all of the above. So for the determination of which component do we use Winkler method or modified Winkler method or azide Winkler method? Yes, it is option A, dissolved oxygen. So dissolved oxygen or DO is typically measured using DO meter, DO probe if it is a field measurement. But in the case of laboratory measurements, we go for Winkler method or azide Winkler method. So we'll see how they are. So diometer is nothing but a direct measurement device which will give a analog or digital display of the dissolved oxygen value. Whereas bioprobes, the dissolved oxygen probe works on the basis of oxidation reduction reactions or redox reactions, providing continuous and live measurements. So they work on the principle of oxidation reduction. Also, the probes will have mostly an applied voltage, so they require a warm up time before we use it for the measurement. During this warm up time, the electrodes are polarized and Once we connect to the meter, electrode sensor is dipped into the solution being tested. So we will dip the probe into the solution, and then voltage can be applied to the electrodes inside. The oxygen molecules reaches the membrane, reaching the electrodes through the permeable or semi-permeable membrane via diffusion. So then, obviously, a small electrical current will flow between the electrodes, that is between cathode and anode, and the amount of current flowing between electrodes is proportional to the oxygen concentration of the solution. So that is how DO is typically measured. So once the meter is calibrated, by measuring the current flow, we can measure the dissolved oxygen amount. But the disadvantage with the this particular method is that from the solution, it will consume a part of oxygen which is equal to diffusion in the sensor. So whatever value it is giving, that will be lesser than the actual dissolved oxygen in the solution, because some amount will be reduced near the dissolved oxygen probe. So if we have to obtain an accurate measurement, if we are using a galvanic probe, then we have to stir the DO probe in the solution. So the next method, that is Winkler method, which we use in uh, laboratories. So this, sorry, one second. Okay, yeah. So next we have Winkler method and Aside Winkler method. After explaining Winkler method, we'll go to modified Winkler method or Aside Winkler method. Yeah. So Winkler method. So here, what we are doing is, um, this is performed on site, as delays between sample collection and testing may result in an alteration in oxygen content. So dissolved oxygen is always considered as a indicator of a health of water body, because for each fauna and flora that is there within the aquatic environment, there is some requirement of minimum dissolved oxygen in that particular water body. So we always need some amount of dissolved oxygen to be maintained, and so we have to occasionally test the available dissolved oxygen. So here in Winkler method, we use titration to determine dissolved oxygen in the water sample. So a sample bottle is filled completely with water, that is, we from the site we'll take the sample in a bottle, in a sampling bottle. So as you know, whenever we are using a sampling bottle, it should be rinsed with the same liquid that we are going to test. So it should be rinsed thoroughly with that particular sample water itself, and then it is filled completely with water. That is, we should ensure that there is no air is left, otherwise some error may come up in the result. So because already some amount of air will be there, means that will give us an erroneous result. Okay, so it should be completely filled, and then dissolved oxygen in this particular sample is then fixed by adding a series of reagents to form an acid compound which is then titrated with a neutralizing compound to get a color change. So first we will add some reagents and make it to an acid compound. Then we'll add a neutralizing agent and titrate it till we get a color changing point. And that point of color change is termed as end point. This particular terms are common in all the titration methods. So whenever there's a color change or a disappearance of color, that particular point that we call it as end point. And this, in the case of Winkler method, will coincide with the dissolved oxygen concentration in the sample. And dissolved oxygen analysis best done in the field, as the sample will be less altered. So the thing is, it's not an on-site test, complete on-site test, but we need to perform it at the earliest once the sample is collected. The titration should be done at the earliest. So in the Hazard Winkler method, this is also similar to Winkler method, except that the components that we are adding during titration may slightly change. So here also we have to fill the sampling bottle with the water sample without any air. Then we have to convert it into an acid. That's a fix. We have to fix it. For that, we'll use manganese sulfate, alkali iodide azide, and concentrated sulfuric acid. And then we have to neutralize it, as I told earlier. So we'll use sodium thiosulfate to titrate, and then the color changes to a pale yellow color, that is our change point or the end point. And then we'll add starch as indicator to finish titrating with sodium thiosulfate until clear. And the amount of sodium thiosulfate required to neutralize our acid compound is the dissolved oxygen. So the terms and methods are same. Only thing is the compound that is used is particularly mentioned here as alkali iodide azide, manganese sulfate, and concentrated sulfuric acid. That's azide Winkler method or modified Winkler method. All right. Moving on to the next question. Question number 10. Match the different types of water pollution to the most likely pollution sources. Option A 1A, 2D, 3B, 4C. Option B 1D, 2A, 3B, 4C. Option C 1D, 2B, 3A, 4C. Option D 1D, 2A, 3C, 4B. So in the first column we have the Roman numerals 1 to 4, that is nutrient pollution, nitrates and phosphates. Second we have toxic and hazardous chemical pollutants. Third we have microbiological pollution. Fourth we have heat pollution, increased water temperature. And in the second column we have A. Landfill leachate, B. Untreated or partially treated wastewater effluent, C. Industrial runoff, D. Runoff from agricultural field. So, which particular pollutant is coming from which source? We have to match accordingly. So, I have option B in the answer and the chat box. Yes, correct option is option B, that is 1D, 2A, 3B, 4C. So nutrients, for example nitrates, phosphates, all these comes from applied fertilizers in the farms or field. So once we apply fertilizers containing the nutrients required for the plant bodies, they will reach the soil. Some amount will be absorbed by the crops, some amount will be washed off along with the runoff when we apply irrigation water. So the primary source of nutrients like nitrates and phosphates is from the runoff from agricultural fields. Next one, landfill leachate, industrial discharge, acid rain, all these can cause toxic and hazardous chemical pollution in water, because these will have hazardous components in that, which are life threatening, which can be life threatening as well. From the industrial discharge, it can have many hazardous chemicals. Also landfill leachate may have e-waste as well, which in turn can generate some hazardous materials, creating chemical pollution in water. So if we are improperly discharging these into water sources, this can even cause microbiological pollution. Then another one, increased water temperature, which is heat pollution. This can be caused by addition of industrial runoff to water sources. Because if after some cooling process, the water jacket that is used to cool that equipment may be directly discharged into a water body. So this hot water discharge may suddenly increase the temperature of that particular water body, leading to heat pollution, leading to what is called heat pollution. So let's see one by one source of water pollution. So as you can see, there is point source of water pollution as well as non-point source of water pollution. So non-point source of water pollution includes farm, agricultural field, golf course, etc., where we are applying fertilizers, pesticides, herbicides, etc., for the growth and protection of our crops, golf lawn, etc. Another non point source of water pollution is residential neighborhoods and urban streets. From there, chemicals, oil, grease, or some other, in the case of cold countries, we will spread salt on the winter roads to remove the snow. So maybe that also can end up in the water body. So all these happen to be non-point source of water pollution. Also abandoned mines, construction sites, all these are non-point source of water pollution. Now point sources or point discharges happen usually from animal feeders, also and sewage treatment plants, industries, factories, disposal sites, all these form the point source of water pollutions, because they are typically generated at a particular source at a particular point and is directly discharged into the water body without proper treatment. All right. So, as we saw earlier in the first question, we have three different categories of classification of water pollutants. On the base of pollutant sources, we have industrial pollutant, agricultural pollutant, urban pollutant, and natural, geogenic, or biogenic pollutant. On the basis of degradation nature, we have degradable or non conservative or reactive pollutants, and non degradable or conservative or non reactive pollutants. And on the basis of physical and chemical characteristics, we have classified the type of water pollutant as physical pollutant, chemical pollutant, and biological pollutant. So now we'll see what are the major types of pollution. So the types of water pollution, so here we have a tabular column with types of water pollution, cause of pollution, symptoms, effect, and source. We'll see them one by one. First one is biodegradable waste. Biodegradable waste is generated by humans and animals. So once this is discharged into a water body without proper treatment, it will result in a reduced number of flora and fauna and may increase the number of bacteria. So the effect will be bacteria level increases, dissolved oxygen decreases, so thereby it will lead to death of aquatic life. Major source of biodegradable waste is runoff and improperly treated effluents. So the second type of water pollution is nutrients, that is nitrates, phosphates, etc. So once these are present in water, we can see that the water is stinky, turbid with greeny or cloudy or slimy appearance. This will lead to the growth of algae blooms, leading to eutrophication of water source. So this particular thing, as we saw earlier, is primarily due to the overuse of fertilizers or over irrigation, which may lead to heavy runoff. Also due to improper disposal of containers having these fertilizers, etc. All right. So the third one is heat, that is increased water temperature. This will also reduce the dissolved oxygen and will cause in the death of fish and plants. This is particularly due to the discharge from improperly treated effluent from industries. Next one is sedimentation. Sedimentation is like suspended particles will be settling down. So the water becomes more turbid, water becomes warm, depth of water source will be decreased, and toxins will start getting deposited along with these sediments. So the primary source of this pollution is construction site, farming and livestock operation, logging, flooding, city runoff, dams, etc. Next one is chemicals. So they can be toxic and hazardous chemicals as we saw earlier. So the presence of chemicals is detected by stinking smell, cloudy appearance or colored appearance, death of life, aquatic life, and this may even lead to diseases for humans, may lead to birth defect, infertility, cancer, etc. So these chemicals are usually human made and they result ending up in water bodies due to improper handling by human. It can be due to runoff, it can be from landfill leachate, acid rain, industrial discharge, etc. Then we have radioactive pollutants caused by radioactive isotopes. So, the presence of radioactive isotopes will lead to increased rate of birth defect, cancer, etc. in human and animal population. It can destroy the flora, fauna as well as human life. Radioactive pollutants typically reach the water source from the effluent discharge from factory, industry, hospitals, urban areas, uranium mines, etc. Then we have the medical type of pollution caused by medicines and antibiotics. This will cause infertility in aquatic organisms and other symptoms may happen. This is particularly again a human made pollution wherein humans dump the medicines into water system or improper effluent discharge from hospitals, medicine manufacturing units, etc. Last, we have microbiological pollution due to bacteria, virus, and protozoa. So, this can lead to gastrointestinal disorders in animals and humans, and the water becomes non palatable, that is, we cannot drink that water. So, this is due to improper treatment or defective treatment units and may even occur naturally. So, here in this table, we have common water pollutants and their sources. So this is also given in the, these are all given in the NPTEL, that lecture videos as well. Uh, all right. So we'll move on to the next question. Question number 11 to 13, we have a common statement. A 5-meter deep clarifier in a water treatment plant treats 25 million liters per day of raw water per day. The volume of clarifier is 250 meter cube and its length to width ratio is 4.5 is to 1. Assume density and dynamic viscosity of water as 1 into 10 raised to minus 3 Newton second per meter cube and 1000 kilogram per meter cube, and specific gravity of particles are 2.65. Answer the following questions based on the given information. So we are given a deep clarifier, 5-meter deep clarifier, and per day it treats 25 mld. The total volume of the clarifier is 250 meter cube. Length to breadth ratio is 4.5 is to 1. Dynamic viscosity, density of water, and specific gravity of particles are given. So, the first question is to determine overflow rate of the clarifier in meter cube per meter square per day. So, I'll wait for 3 minutes because this is not that complicated question. Direct substitution in the equation only. So, I'll give you 3 minutes and then we'll see how to solve this. Please put your answers in the chat box. Okay, we'll see how to solve the question. So the correct answer is 500 meter cube per meter square per day. So we are given that the depth of the clarifier is 5 meter. The quantity of raw water treated per day is 25 mld. Volume of clarifier is 250 meter cube. Length to width ratio is 4.5 is to 1. Density of water is 1000 kilogram per meter cube. Dynamic viscosity is 1 into 10 raised to minus 3 Newton second per meter cube. And specific gravity of particles is 2.65. Now we are asked to determine the overall flow rate, right? So the flow through each clarifier is 25 mld, that is 25 into 10 raised to 3. Now area of the clarifier will be, we are given that the volume is 250 and the depth is 5. So the area of clarifier will be 250 by 5, which is 50 meter square. Now overall flow rate is, velocity V is discharge by area, that is 25 into 10 raised to 3 by 50, that is 500 meter cube per meter square per day. Hope that is clear. Moving on to the next question, that is, determine the minimum diameter of particles that can be removed with 100% efficiency. Determine the minimum diameter of particles that can be removed with 100% efficiency. So all other parameters remain the same. That is, I'll put that slide for easiness. So all these data is given. We are asked to determine the minimum diameter of particles that can be removed with 100% efficiency. Okay, I'll wait for another 2 minutes and then we'll see how to solve this. So the data is shown in the slide. It's the same data as in the previous question. So please solve it and type in the numerical value in the chat box. Okay, let's see how to solve this. Yeah. So the correct answer is 0.080 mm. So we are given the same details as in the previous question, that is 5-meter deep clarifier with 25 mld water being treated every day, and the volume of clarifier is 250 meter cube with length to width ratio of 4.5 is to 1. So density of water, dynamic viscosity and specific gravity of particles are same as in the previous question. And one more additional knowledge we know from the previous question, that is overflow rate. We have calculated it as 500 meter cube per meter square per day, or which is equal to 0.005787 meter per second. Right. So here we are asked for 100 percentage efficiency. So for 100 percentage efficiency, VO should be equal to VS. That is, VO should be equal to VS means our overflow rate should be equal to settling velocity. So that will be VO equal to rho W into G into S minus 1 D square by 18 mu. So now we know the value of overflow rate from the previous question. So, so substituting the non-values, we have 0.005787 is equal to 1000 into 9.81 into 2.65 minus 1 into d square, the whole divided by 18 into 0.001. So solving for d, we will have d is equal to square root of 0.005787 into 18 into 0.001 divided by 1000 into 9.81 into 2.65 minus 1. So these things all comes under the division itself. So we need to take the square root of this particular value, which will give d as 0.080221 mm. Hope that is clear. So the next question is, determine the horizontal velocity of particles and water in the tank. So we need to determine the horizontal velocity, VH. Please solve and put the numerical in the chat box. So since I'm not seeing any numerical answers in the chat box, I think without wasting time, I'll explain how to solve this. So the correct answer is coming around 0.019 meter per second. So again, the same values we have. I'm not repeating the same because it's the same as the previous question. So we are given that length to breadth ratio is 4.5 is to 1. And we know that area is length into breadth. So area is given as 50 meter square So that is equal to 50 meter square is equal to 4.5 into b square. Since length to width ratio is 4.5 is to 1. L by B is 4.5 is to 1, or L is 4.5B. That's why 50 is equal to 4.5 B square, substituting for L. Now from this we'll get B as 3.33, that is square root of 50 by 4.5. Right. So, sorry. So we know that the horizontal velocity VH is equal to flow rate Q or discharge Q divided by BH, B into H. So here we have determined B as 3.33. So substituting the value in the equation, BH is equal to 25 into 10 raised to 3 divided by 3.33 into 4.5. Substituting, we'll get it as 1668.335 meter per day, or converting into meter per second, we have 0.0193 meter per second. Hope that is clear. Moving on to the next question, question number 14. Which of the following statements are false regarding the aeration during drinking water treatment? Statement 1. Precipitation of dissolved ions in raw water is facilitated through aeration. Statement 2. Turbidity and suspended solids in raw water are significantly reduced through aeration. Statement 3. Aeration is a major treatment process at the treatment plant for water withdrawn from groundwater sources. So, option A, statements 2 and 3. Option B, statement 1 and 3. Option C, statement 2. Option D, all statements are false. So, we are asked to determine the false statements among the three. Yes, so the correct answer is option C, that is statement 2. So, aeration can be used for precipitation and removal of iron and manganese. It's ineffective for turbidity or suspended materials, and it may not be used for surface water, so may or may not be used for surface water sources. However, at the treatment plant, it is the first major process for water withdrawn from groundwater sources. Moving on to the next question, question number 15. A drastic reduction in settling velocity is typically observed in which zone of settling? Option A, type 1 discrete settling. Option B, type 2 flocculent settling. Option C, type 4 compression settling. And option D, type 3 hindered settling. So, in which of the settling zones do we have drastic reduction in settling velocity? The correct answer is option C, type 4 compression settling. This occurs when the particle's concentration is so high that particles at one level are mechanically influenced by particles at the lower level. So then the settling velocity reduces. Okay, so let's see what is sedimentation, settling, or clarification. So it is the phase separation process wherein the suspended materials, for example, clay, silt, organic matter, etc., settles down under the effect of gravity. So the suspended material may be particle that is originally present in the source of water, for example, clay, silt, etc. Then we go for plain settling or primary settling. But if the particles are flocks created due to coagulation flocculation process, then we have to go for chemically assisted, sorry, coagulant assisted settling or chemical added settling. And if the suspended material is biomass that is produced in biological treatment unit or the wastewater treatment unit, then we have to go for secondary settling. So for settling, what we mainly do is we'll reduce the velocity of flow to a level to which the water won't be able to carry the load in suspension. So gravity pull will be more and then it starts settling. So we have four zones of settling starting from discrete or free settling, type 1, then type 2 settling or flocculent settling, type 3 or hindered or zone settling, and type 4 or compression settling. So type 1 or discrete or free settling occurs when the particle is settling without any interaction among themselves. So this happens at low solid concentration, as in the case of removal of sand particles. Then type 2 settling or flocculent settling. Here, initially the particle will start settling independently, but at a particular depth, they will combine together or they will flocculate or coagulate, and then velocity of settling particles increases as the size of flocculant increase, because as the size increase, gravity force will be more and will have a larger settling velocity. Then we have type 3 hindered or zone settling. Here interparticle forces are sufficient to hinder the settling of neighboring particles. So with respect to each other, they will tend to be in a fixed position. And this is typical in the settler for activated sludge process. That is secondary clarifier that we use in the settling of biomass suspended materials. Type 4 or compression settling. This occurs when the particle concentration is too high that the particles at one level are mechanically influenced by the particles on the lower level. So then the settling velocity drastically reduces as we saw in the question. So with that, we have come to an end for the today's discussion questions. So if we don't have any other doubts, we can close the session for today. So now I'll stop the presentation. Okay. So if we don't have any other doubts, we can close the session for today. Okay. All right then. Okay, then we'll meet during the next session next Tuesday at 7 o'clock. Thank you all.